Hello and welcome to Whispers of Earth, where wonder meets the night, and science gently guides us through the vast mysteries of existence. Tonight, we embark on a tranquil journey toward one of the most thought-provoking and mysterious questions we face, not just as curious minds, but as human beings contemplating our place beneath the stars. It's a question that has fascinated us all. What is guiding us, and what is the true nature of our connection to the cosmos? Tonight, we step into a journey unlike any other, a story written not in books or on the internet, but in the very stones beneath our feet, in the mountains that rise against the sky, and in the oceans that whisper against the shores. We are about to drift backward, farther than dinosaurs, farther than the lush forests of Earth's youth, farther even than the mighty supercontinent we all know as Pangea. We are venturing into the forgotten worlds before Pangea, into landscapes that challenge imagination and carry us to the edge of deep time itself. Before we begin wandering across those lost continents, I want to bring this moment closer to you. Where are you listening from right now? Perhaps you're curled up late at night beneath the comfort of a blanket, searching for calm. Maybe it's an early morning, with a mug of warm tea in hand, your mind just beginning to open to the day. Or perhaps you've stumbled upon this story during the rhythm of an ordinary afternoon, looking for a pause, a breath of wonder. Wherever you are, whenever you are here with me, and together we'll walk hand in hand through the corridors of Earth's deep history. Think of this: billions of years of change, all woven into the fabric of one planet. Continents have shattered and reunited. Oceans have drained and returned. Climates have boiled with unbearable heat and frozen into silence. And yet, through every cycle, Earth has endured, reshaping, reinventing, and presenting new faces to the sky above. The world we call home is not fixed. It is restless, alive, always sculpting itself in patterns that unfold over spans of time so vast they seem impossible to us. This story will not be a race. There will be no sudden bursts of noise, no frantic pace. Instead, we will stroll gently, noticing the small details the way you might notice leaves scattered along a quiet path, or the way stones catch the light on the edge of a river. We will let Earth reveal herself slowly, for she has always moved slowly. Her minutes are our millennia, her hours our ages. Let us begin with what feels familiar: Pangea. You may already picture it, a single vast continent where today's puzzle pieces of land once fit together like old friends reuniting. South America nestled against Africa, North America drifting close to Europe, India pressing upward into Asia. We know this image. We've seen it drawn in books and imagined in classrooms. Dinosaurs roamed its plains, forests cloaked its valleys, and rivers cut through its heart. Pangea was immense, stretching nearly from pole to pole. And yet, here lies the twist. Pangea was not the beginning of Earth's great continental story. It was only the latest chapter in a cycle older than forests, older than animals, older even than the first whispers of complex life. Earth, you see, has always been a recycler, drawing her lands together, tearing them apart, and gathering them once more. So if Pangea was only the last gathering, what came before? What forgotten continents shaped the stage of life before even dinosaurs had their chance to rise? To answer, we must journey deeper into time, beyond what feels imaginable, into worlds erased, worlds almost alien. To understand Earth before Pangea, we must first accept a truth both humbling and awe-inspiring. Continents are not eternal. They are wanderers, drifting slowly across the planet like rafts on a vast, unseen ocean. What feels solid beneath our feet today, mountains, valleys, coastlines, is only temporary. A fleeting arrangement in a grand dance that has been unfolding for billions of years. This dance is guided by plate tectonics, a process as steady as the heartbeat of the planet itself. Beneath the crust, the mantle churns with slow, powerful convection currents. Heat from Earth's interior stirs the molten rock, tugging the rigid plates above like pieces of an ever-moving puzzle. Over millions of years, this restless energy forces continents apart, then draws them together again, colliding with enough force to build mountains taller than Everest, splitting open oceans only to swallow them back into the deep. Imagine the continents as travelers in a story that has no final page. They drift apart, journeying alone across wide seas. Then, over unimaginable spans of time, they are pulled back toward one another, like dancers returning to the same embrace. This rhythm is called the supercontinent cycle, and Pangea was only the most recent step in that endless waltz. Scientists know this not from guesswork, but from clues hidden in the ancient bones of the Earth. Rocks carry magnetic signatures, tiny mineral grains frozen in place as they cooled, recording where they once sat relative to the magnetic poles. Fossils of identical species appear on continents now separated by oceans, telling us they were once neighbors. Mountain ranges line up like scars across lands now distant, proof of collisions long ago. Together, these fragments reveal a history written across billions of years. And that history tells us something extraordinary. Pangea was not the first, nor the second, but only the latest in a long line of supercontinents. Before Pangea came Rodinia. Before Rodinia came Nuna. Before Nuna came Kenorland, and perhaps even before that, smaller protocontinents like Ur, fragile and almost mythical in their antiquity. Each of these vast landmasses rose, thrived for a time, and then shattered, scattering their fragments into new oceans. Consider the timescales involved. If you were to compress Earth's 4.5 billion year history into a single day, Pangea would appear only in the final minutes before midnight. All of human history, The rise and fall of civilizations, the stories written in our oldest myths, would last no more than a blink. Even the age of dinosaurs, mighty as it seems, was only a passing chapter compared to the eons when other supercontinents ruled. The deeper we go, the stranger these worlds become. Rodinia existed when there were no forests, no animals on land, no flowers to scent the air. Nuna came even earlier, a world almost barren except for microbial life clinging to the edges of ancient seas. Kinorland rose in an earth still learning to breathe oxygen, and beyond them a fragment so small, so ancient, that it feels like a legend written in stone. The continents were the main characters in these dramas. Life was simple, the skies unfamiliar, the climates extreme. But though the stage seemed bare, the play was immense. Eruptions that burned for millions of years, oceans that swallowed whole continents, ice sheets stretching from pole to pole. These were the forces that shaped not just the land, but the destiny of life itself. If Pangea is the supercontinent we know best, then Rodinia is the one history almost forgot. Its name comes from the Russian word for motherland, and how fitting that is. For Rodinia was a birthplace of sorts, a union of nearly all Earth's land that set the stage for future worlds. Yet unlike Pangea, there were no dinosaurs striding across its plains, no forests swaying in its winds, no birds calling overhead. Rodinia was a barren, alien land, ruled not by animals or plants, but by silence, stone, and time itself. Rodinia formed roughly 1.1 billion years ago, long before the first fish darted through the seas or the first plants clung to the shore. Continents collided with unstoppable force, welding together into a cluster so vast it dominated the face of the planet. But to imagine standing there is to step into a world stripped of everything familiar. No green canopies overhead, no flowers to sweeten the air. Only vast stretches of rock and sand, fringed by shallow seas alive with microbial mats. The evidence of Rodinia's existence comes from scattered fragments, ancient cratons preserved in North America, Siberia, Australia, China, and beyond. Like shards of a shattered mirror, these rocks, when studied, reveal magnetic signatures and mineral clues that point back to a single configuration. The exact arrangement is still debated. Some reconstructions place North America at its center, surrounded by fragments that would later become South America, Africa, and Australia. Others imagine different orientations, with the pieces rotated or flipped. The truth is likely lost in the erasures of time, rocks subducted, mountains eroded, clues forever scrambled. And yet, even if we cannot map it perfectly, we know Rodinia was real. We know it gathered Earth's lands into a unity larger and stranger than anything alive today could fathom. And we know its existence profoundly shaped the future. For while Rodinia stood, the atmosphere was changing. Tiny cyanobacteria, working tirelessly in shallow seas, were pumping oxygen into the air. This was the era of the Great Oxidation's aftermath, when oxygen levels, still fluctuating, began to tip the balance of climate and chemistry. Without forests or soil, the interiors of Rodinia may have been deserts, scorched by summers, frozen by winters, far removed from the moderating breath of the ocean. Along its coasts, shallow seas hosted microbial ecosystems that slowly resculpted the air, preparing it for the life yet to come. Rodinia lasted for hundreds of millions of years before rifting apart around 750 million years ago. And that breakup was catastrophic. As the great landmass tore, new oceans opened, carbon dioxide levels plummeted, and the world may have been plunged into one of the most extreme climate events in Earth's history. Snowball Earth. Imagine ice stretching all the way to the equator, seas frozen solid, continents buried in glaciers. Life clung on in thin ribbons of refuge, sheltered near volcanic vents, or under translucent layers of ice where sunlight still seeped through. Rodinia, in its assembly and destruction, was not just a geological chapter. It was a biological turning point. Its rise gathered the continents. Its fall may have triggered the environmental stress that forced life toward greater complexity. Without Rodinia, the trajectory of evolution might have been entirely different. Before Rodinia, there was another vast gathering of Earth's drifting lands. Scientists call it Nuna, though you may also hear the name Columbia. It came together nearly 1.8 billion years ago, so unimaginably ancient that even Rodinia feels like recent history by comparison. Nuna was one of the first great attempts by Earth to unite its scattered continents into a single monumental landmass. To picture Nuna is to stretch imagination past its limits. There were no animals yet, no forests, not even moss to soften the rocks. The land was bare, mostly raw stone and volcanic plateaus. Along the coastlines, microbial mats, thin films of life clinging to damp surfaces, were the only pioneers. The seas, however, told a different story. Cyanobacteria drifted in colonies, building stromatolites, layered rock structures that still exist in places like Western Australia today. These microbes, humble and tireless, were exhaling oxygen, slowly reshaping the chemistry of the oceans and sky. Nuna's assembly was no small feat. Ancient cratons, stubborn pieces of Earth's oldest crust, collided over millions of years, welding into a single continent. The scars of these collisions remain visible in places like Canada, Greenland, and Siberia. Mountain belts, now eroded into their roots, tell us that titanic forces once shoved rock against rock, raising ranges that towered over a lifeless land. The arrangement of Nuna is still debated, but evidence suggests it linked much of what we now call North America, Greenland, Scandinavia, Siberia, India, Australia, and South America. It stretched across a huge portion of the globe, gathering most of Earth's land into one formidable cluster. Imagine a world map where familiar outlines exist, but in alien positions, joined in ways we would never expect. The climate of Nuna was equally strange. With such a vast interior far from the sea, deserts likely spread across its heart. Rainfall was scarce, temperatures extreme. The coasts, by contrast, may have supported shallow seas rich in microbial life. Volcanic activity was frequent, rifts occasionally tearing at Nuna's edges and releasing gases that altered climate. Oxygen levels were beginning to rise, but slowly, haltingly, just enough to create ripples in the chemistry of Earth's systems. This was the so-called boring billion, an era often described as uneventful from a biological perspective, because evolution appeared to crawl rather than leap. Yet that label hides the truth. Beneath the surface, the stage was being prepared. Oxygen levels were stabilizing. Continental platforms provided stable, shallow seas where life could slowly diversify. Mineral deposits formed, resources that, billions of years later, humans would mine and depend upon. Nuna may not have dazzled with sudden bursts of life, but it laid the foundations for everything that followed. Eventually, around 1.5 billion years ago, Nuna began to fracture. Rifts opened, seas flooded in, and the great landmass scattered into pieces. But its legacy endured. Later supercontinents, like Rodinia and Pangea, were built partly from the remnants of Nuna. In that way, Nuna was not just a continent, but a cornerstone, one of Earth's earliest grand experiments in gathering its lands together. Long before Nuna, before Rodinia, even before Pangea was a dream in the planet's restless heart, there was Kenorland. It is one of the earliest true supercontinents we can identify with some confidence, forming roughly 2.7 billion years ago. To imagine Kenorland is to step into a world so alien that it feels almost mythological. The sun was dimmer, shining with only about 3/4 of its modern brightness. The atmosphere was harsh and unstable, filled with gases that would suffocate us today. Oxygen was only just beginning to make its first real appearance, thanks to microscopic life working silently in the oceans. Kenorland was not like the continents we know now. It was a patchwork stitched together from some of Earth's oldest cratons, fragments of ancient crust that had survived countless convulsions of the planet. Pieces that would one day form parts of North America, Scandinavia, Southern Africa, and Western Australia were welded together in this early assembly. The collisions that forged it left behind mountain belts, which, though long eroded, still whisper their story in the rocks of Canada, Finland, and South Africa. This was also the time of the Great Oxidation Event, a turning point that changed everything. Cyanobacteria, simple microbes in shallow seas, were exhaling oxygen as a byproduct of photosynthesis. For millions of years, that oxygen was absorbed by iron dissolved in seawater, forming massive deposits of banded iron stone, layers of black and red rock that we still mine today. But eventually, the sinks filled. Oxygen began spilling into the atmosphere, transforming it in ways both wondrous and catastrophic. For the microbial life that thrived without oxygen, this was a disaster. Many perished, poisoned by the very gas that would one day allow complex creatures like us to exist. But for the future, it was the first breath of possibility. The air was still thin, far from breathable by our standards, but it was changing. The planet itself was entering a new era. Kennerland stood at the center of this transformation. Its vast land surfaces altered weathering rates, drawing carbon dioxide from the air and shifting climate. The release of oxygen disrupted methane, a powerful greenhouse gas, cooling the planet and perhaps triggering one of Earth's earliest ice ages, the Huronian glaciations. Imagine ice spreading across a world already barren and strange, glaciers grinding over rocks untouched by trees or grass, while microbial mats clung desperately to thin strips of water that remained unfrozen. And yet, Kenorland was also a builder. The collisions that created it thickened Earth's crust, laying down stable continental roots, cratons that still endure today. These keystones became the foundation for every continent that followed. Without them, Earth's surface might never have gained the permanence required to support forests, animals, or us. Kenorland eventually fractured, beginning its breakup around 2.5 billion years ago. Its fragments drifted apart, scattering across the globe, later to be reassembled into Nuna. But in its brief existence, Kenorland helped reshape the planet's atmosphere, climate, and geology in ways that echo through deep time. Kenorland was a land of firsts. The first great oxygen crisis, the first large-scale glaciations, one of the first experiments in continental unity. It reminds us that Earth's earliest continents were not just land, they were engines of planetary transformation. Before Kenorland, before Nuna, even before Rodinia, there may have been a land so small, so ancient, that it feels more like legend than geology. Geologists call it a name chosen because in many languages it simply means the first or the beginning. If Kenorland was an early experiment in continental unity, then was the seed from which all later continents grew. Is thought to have formed nearly 3 billion years ago, during the Archean Eon, when Earth itself was still young, barely 1.5 billion years old. The planet was hotter then, its crust thinner, and volcanic activity constant. Oceans covered most of the surface, steaming under a fainter sun. Land was scarce, fragile, and easily swallowed back into the mantle. Against this backdrop of instability, emerged as one of the first stable fragments of true continental crust, a survivor in a world where survival was rare. How do we know existed at all? We don't have a map, only fragments. Ancient rocks in South Africa's Kaapval Craton, in Australia's Pilbara Craton, and in parts of India and Madagascar bear isotopic signatures more than 3 billion years old. These are among the oldest surviving rocks on Earth, and when pieced together, they hint at a coherent landmass that may once have stood alone as What would have looked like? not like the continents we know today. There were no forests, no rivers lined with grass, no moss to soften the ground. Its surfaces were barren stone, perhaps coated in thin microbial films. The air was unbreathable, rich in methane and carbon dioxide, with only a trace of oxygen. The skies may have been hazy and orange, tinted by atmospheric chemistry. Along the coasts, shallow seas nurtured microbial mats and stromatolites, layered communities of cyanobacteria slowly exhaling oxygen into a world not yet ready to receive it. Ur's importance lies not in its size. It may have been only a fraction of modern Africa, but in its persistence. Unlike earlier, smaller proto-continents that were swallowed back into the mantle, Ur endured. For billions of years, its fragments have remained intact, later stitched into larger supercontinents like Kenorland, Nuna, and Rodinia. Even today, pieces of Ur lie beneath our feet, hidden in the bedrock of Africa, Australia, and Asia. To endure through such deep time is astonishing. Oceanic crust is recycled every couple of 100 million years, but continental crust is thicker, more buoyant, harder to destroy. Still, in Earth's hotter youth, even continents were at risk of being consumed. That Ur survived makes it the cornerstone of all that followed. It provided stable ground for life to cling to, shallow seas for microbes to expand into, and the foundation for the great continental cycles that would reshape the planet again and again. In many ways, Ur was Earth's quiet beginning, a modest land, barren and silent, but crucial. Without it, later supercontinents might never have formed. Without it, the stage for forests, animals, and eventually humans might never have been set. If Ur was the first fragile seed of land, and Kenorland the first great experiment in continental union, then Nuna and Rodinia were chapters in a repeating story, a story that has defined Earth's history for billions of years. This story is known as the supercontinent cycle, a rhythm as steady and inevitable as the beat of a heart. Imagine Earth's crust as a cracked eggshell, broken into plates that drift slowly atop the mantle. Heat rises from the planet's interior, setting the mantle into motion like thick syrup stirred from below. That motion tugs at the plates above, forcing them apart in some places, squeezing them together in others. Over immense spans of time, the scattered continents wander across the globe, collide, and merge into a supercontinent. For a while they remain fused, one immense landmass surrounded by a global ocean. But the story never ends there. Heat builds beneath the vast continent, rifts open, and the land fractures into pieces once again. Oceans flood in, the continents scatter, and the cycle begins anew. Each cycle unfolds over 400 to 600 million years. That is longer than the age of the dinosaurs, longer than the lifespan of most animal groups. In Earth's 4.5 billion year history, several complete cycles have already passed. Ur grew into Kenorland. Kenorland broke apart and reassembled into Nuna, Nuna scattered and merged into Rodinia, and eventually Rodinia gave way to Pangea. And even now, the continents we live on are still drifting toward the next reunion, sometimes called Pangea Proxima, which may form 200 to 300 million years from now. This rhythm is not just geology, it is life itself. Every time continents gather into a supercontinent, the world changes. The vast interiors of these landmasses grow arid and extreme, far from the moderating influence of the sea. Climate swings become sharper. Oceans lose their familiar currents as circulation patterns are disrupted. And when the continents break apart again, shallow seas flood in along the rifts, creating warm, fertile environments where life flourishes and diversifies. Consider the snowball Earth events that may have been triggered by Rodinia's breakup, or the Cambrian explosion that followed not long after, when new coastlines and shallow seas provided the perfect stage for life to diversify in spectacular ways. Even the rise of forests during the Carboniferous and the mass extinctions that reshaped marine life were tied to the rhythms of continents assembling and breaking apart. The land does not simply hold life, it directs it. Geologists uncover this rhythm through scraps of evidence, magnetic signatures in ancient rocks, mountain belts that line up across now distant continents, fossils of identical organisms found on lands separated by oceans. Each clue is a piece of a vast puzzle, and when assembled, they reveal a truth almost beyond comprehension. Earth is never still. It has always been a planet in motion. The ground beneath us may feel permanent, but it is not. Every continent we know, Africa, Asia, the Americas, carries scars of ancient collisions, whispers of long-vanished oceans, fragments of supercontinents that no human eye ever saw. We are living in the latest verse of a song that has been playing for billions of years. If continents are the dancers in Earth's endless waltz, then oceans are the spaces between them, the stages that open and close, shaping the rhythm of the performance. Every supercontinent cycle leaves behind not only mountains and scars, but also the ghosts of oceans that once existed and then disappeared. These oceans, now gone, are remembered only through whispers preserved in rocks. Take the Iapetus Ocean, for example. It opened roughly 600 million years ago, stretching between what would later become North America, Europe, and parts of South America. For over 200 million years, it teemed with life. Trilobites crawling across the seafloor, brachiopods filtering water, and the first primitive fish darting in shallow waters. Eventually, tectonic plates drew the surrounding continents back together. The Iapetus closed, its death marked by the rise of mountain chains such as the Appalachians in North America and the Caledonides in Europe. Today, those ranges, long eroded, are the silent tombstones of an ocean that no longer exists. And Iapetus was far from the first. Before it came Merovia, the global ocean that surrounded Rodinia nearly 1 billion years ago. Later, during the time of Pangea, there was Panthalassa, a vast body of water covering nearly 3/4 of the globe, encircling the single supercontinent like a cosmic moat. The Tethys Ocean, meanwhile, once stretched between Gondwana in the south and Laurasia in the north. Its closure gave birth to the Mediterranean Sea, the Alps, and the Himalayas. Each of these vanished oceans played its role, altering climates, nurturing ecosystems, and leaving traces that scientists painstakingly decode. But how do we uncover the existence of seas that disappeared hundreds of millions or even billions of years ago? The answer lies in geology's subtle clues. Rocks carry magnetic signatures, tiny compass needles frozen into place as minerals cooled, that reveal where they formed relative to Earth's poles. When scientists compare these signatures across continents, they can reconstruct how those lands once fit together and which oceans must have opened or closed between them. Other clues come from orogenic belts, the crumpled remains of mountains formed when oceans closed. The Appalachians in North America, a line with mountains in Scotland and Scandinavia, proof that those continents were once neighbors, stitched together after an ancient ocean vanished. Fossils, too, tell the story. Identical species found on distant lands confirm that oceans separating them today were once absent, their shores connected in a single ecosystem. Imagine standing on the shore of one of those ancient oceans. The waves would sound familiar, the salt tang in the air the same, but everything else would feel alien. The beaches would be barren, no grasses waving in the wind, no animals leaving tracks. The life was in the water, trilobites scuttling, stromatolite reefs building oxygen, strange arthropods swimming with bodies so bizarre they seem almost unreal today. And yet these oceans, now gone, shaped the course of life as profoundly as any mountain or forest. Every vanished sea reminds us that oceans are not eternal. They are born when continents split, thrive for hundreds of millions of years, and then disappear when continents reunite. But water itself, life's eternal medium, remains. It shifts shape, but never disappears. Through every cycle, the oceans have carried life forward. When we imagine Earth's past, we often picture the land or the seas because they feel tangible. But just as important is the sky, the invisible blanket of gases that has always decided what kind of world Earth could be. And here is the truth. The sky we know today, blue and breathable, is not the sky Earth always wore. For most of its history, the atmosphere was alien, shifting between states that would have killed us in an instant. The earliest atmosphere, more than 4 billion years ago, was thin and fleeting, made of hydrogen and helium, the lightest gases in the universe. But Earth's gravity could not hold them for long. They drifted away into space, leaving the planet bare. What came next was born from Earth itself. Volcanic eruptions belched out carbon dioxide, nitrogen, methane, water vapor, and ammonia. This was the secondary atmosphere, dense, hot, and toxic. No oxygen to breathe, no ozone to shield the surface from ultraviolet radiation. The skies may have been hazy, tinted orange or red by methane, much like the atmosphere of Saturn's moon Titan today. And yet, this toxic cloak may have been a blessing. The young sun shone dimmer, only about 70% as bright as today. Without strong greenhouse gases, Earth might have frozen solid. Methane and carbon dioxide trapped enough heat to keep the oceans liquid. Those oceans became the cradle of life, shielding the first microbes from the harshness above. Then came the quiet revolution, the rise of oxygen. Around 2.4 billion years ago, cyanobacteria evolved the ability to use sunlight to split water and carbon dioxide, releasing oxygen as waste. At first, this oxygen vanished into the seas, reacting with dissolved iron to form vast deposits of rust-colored rock we now call banded iron formations. But slowly, the sinks filled, and oxygen began spilling into the sky. This was the Great Oxidation Event, and it changed everything. For microbes that thrived without oxygen, it was a catastrophe. Many perished. For the planet, it was a turning point. Methane was destroyed by oxygen, cooling Earth dramatically. Ice spread across the globe, perhaps triggering the Huronian glaciations, some of the first great ice ages in history. But oxygen also paved the way for complex life, making possible metabolisms far more efficient than before. What would those skies have looked like? Before oxygen, hazy, orange, heavy with methane. During the oxygen rise, the skies may have brightened and cleared, though still not the familiar blue we know. Only when oxygen grew abundant enough to form an ozone layer did Earth gain true protection from ultraviolet radiation. With ozone came a new possibility. Life could finally creep onto land, shielded from the deadly rays of the sun. The sky, then, was never passive. It was both sculptor and stage. It shaped climate, controlled which gases warmed the planet, and decided whether life thrived or struggled. It has swung between suffocating haze and oxygen-rich clarity, between greenhouse heat and ice age chill. And all the while, life and atmosphere have danced together, each shaping, each reshaped. For billions of years, life's kingdom was the sea. The oceans sheltered it, fed it, and cushioned it against the harshness of the sky. But eventually, life grew bold enough to test the edges of the unknown, the silent, barren continents. This transition from water to land was one of the most daring experiments in Earth's history. And though it began quietly, its consequences were nothing short of revolutionary. The earliest pioneers were not fish sprouting legs, as we often imagine, but far humbler beings, microbes. Along damp shorelines, mats of bacteria spread across rock, binding grains of sediment with their sticky secretions. These microbial carpets were resilient, able to withstand the drying heat of the sun and spring back to life with the return of water. Fossil evidence hints at these mats more than 1 billion years ago, clinging stubbornly to the edges of rivers and tidal flats. Then, around 470 million years ago, a new wave of pioneers arrived. Plants, not the towering forests we know, but tiny moss-like organisms. They lacked roots, leaves, and wood, but they possessed remarkable adaptations. Their waxy coatings resisted drying. Their spores spread through air currents, reaching new surfaces to colonize. They hugged the ground in low green mats, turning gray rock into patches of life. The arrival of these simple plants changed everything. They slowed erosion, holding soils in place. They created the first thin layers of organic earth, rich with nutrients. Their photosynthesis pulled carbon dioxide from the air and released oxygen, continuing the transformation of the atmosphere. And they offered new homes for other organisms. Fungi, already well adapted to land, formed symbiotic relationships with them. Thread-like fungal filaments helped plants extract minerals from rock, while plants shared carbohydrates in return. This partnership, scientists believe, was crucial for the success of early land plants. Imagine standing on such a shoreline. The land would look bare compared to today. No forests, no meadows, only scattered patches of green clinging to moist cracks and shaded hollows. The tallest plants would barely reach your ankle. And yet, in their smallness, they were rewriting the planet. Soon after, arthropods followed. Millipede-like creatures crept across damp ground, feeding on decaying plant matter. Primitive insects buzzed low to the ground. Their presence was possible only because plants had gone first, paving the way with food and shelter. The impact of these tiny pioneers rippled outward. As plants spread, they accelerated chemical weathering of rocks, drawing down atmospheric carbon dioxide. This cooling effect may have contributed to ice ages during the Ordovician period. They stabilized riverbanks, reshaping waterways into meandering channels. They began to knit together the fragile web of land-based ecosystems. All of this happened quietly, without drama, without spectacle. No towering dinosaurs, no thundering herds, just small green tufts and mats of microbes. But their quiet persistence transformed the continents from barren stone into living landscapes. Every forest, every meadow, every crop field we know today owes its existence to these first, modest colonizers. Once the earliest moss-like plants had claimed the edges of rivers and shorelines, evolution's imagination began to stretch upward. Life was no longer content to cling flat against stone. It began to experiment with height, strength, and complexity. Out of those experiments came something astonishing: the world's first forests. Around 430 million years ago, during the Silurian period, plants developed a breakthrough adaptation: the vascular system. This network of tubes carried water and nutrients through their bodies, freeing them from the constant need to remain in damp places. With vascular systems, plants could grow taller, explore drier soils, and spread farther inland. The first of these pioneers, like Cooksonia, were still small by our standards, only a few centimeters tall, but they pointed the way forward. By the Devonian period, about 390 million years ago, the experiment had reached breathtaking proportions. Trees like Archaeopteris grew up to 30 meters tall, with woody trunks and spreading branches. Imagine walking across land that, for billions of years, had been bare rock, and suddenly finding yourself under a canopy that blotted out the sun. The silence of stone had given way to the whisper of leaves. These first forests transformed the planet. Their roots dug deep into the earth, stabilizing soils and changing the way rivers flowed. Instead of shallow channels washing across barren plains, rivers began to carve meanders and floodplains, guided by the grip of roots. Their leaves intercepted rainfall, slowing the rush of water and nourishing the ground below. Insects and amphibians found shelter in the tangled undergrowth. Fungi thrived among decaying logs. For the first time in history, land became layered with ecosystems, canopies above, understories below, and soils alive with life. But the forests didn't just reshape the land, they reshaped the air. Through photosynthesis, trees pulled massive amounts of carbon dioxide out of the atmosphere and released oxygen in return. Oxygen levels soared, perhaps reaching 30 to 35% compared to today's 21%. The air grew richer, fueling giant arthropods, dragonflies with wingspans nearly a meter wide, millipedes over 2 meters long, scorpions the size of cats. They thrived in this oxygen-rich world, their bodies growing to sizes impossible today. The burial of plant material also changed Earth's chemistry. When trees died and fell into swampy soils, decay was often incomplete. Layer after layer of plant matter accumulated, compressed by time and pressure into vast deposits of coal. The very fuel that humans would one day mine and burn was sunlight captured by these first forests hundreds of millions of years ago. The rise of forests also cooled the climate. By drawing down carbon dioxide, they reduced the greenhouse effect, leading to ice ages during the late Devonian and Carboniferous periods. Life on land expanded, but at the same time, ecosystems were tested by dramatic climate shifts. Extinctions swept through the seas, reshaping marine life. On land, amphibians diversified, and reptiles began their first steps toward dominance. Forests were more than scenery. They were engines of change, altering atmosphere, climate, water, and life. In a world once barren, forests made Earth look alive for the first time. With forests rising across the continents, a new stage was set. Shadows spread where once only bare rock had gleamed in the sun. Oxygen filled the skies to levels higher than at almost any other point in Earth's history. And into that atmosphere stepped creatures unlike anything alive today. Giants born of air rich with breath, forests thick with food, and swamps teeming with opportunity. This was the Carboniferous period, roughly 359 to 299 million years ago, and it was the age of the giants. Among the most astonishing were the arthropods. Today, insects, millipedes, and spiders are small, bound by the limits of their breathing systems. But in the Carboniferous, when oxygen levels soared to 30 to 35%, those limits expanded. Imagine a dragonfly with a wingspan nearly a meter across, Meganura, the ruler of the ancient skies. Its compound eyes glittered in the forest light as it soared above swampy canopies, hunting other insects in aerial pursuits that would have seemed thunderous to the silence of earlier ages. On the forest floor crawled Arthropleura, a millipede-like creature stretching up to 2.5 meters long. With armor-plated segments and hundreds of legs, it scuttled through the undergrowth, feeding on decaying plant matter. Picture walking through a carboniferous swamp, only to hear the rustle of leaves and see a creature longer than you sliding past, its legs rippling in waves. It had few predators. Its sheer size was protection enough. Scorpions, too, grew massive. Some reached lengths of half a meter, their claws snapping shut on prey in the damp, dimly lit forest floor. Even spiders and centipedes swelled far beyond modern relatives, ruling the shadows beneath towering ferns and lycopods. Insects flourished, their diversity exploding alongside the forests. Early cockroaches skittered through leaf litter. Primitive grasshoppers and beetles buzzed and crept. For the first time, the land was not silent. It hummed with wings, clicked with mandibles, and crackled with the sound of countless tiny lives. And these forests didn't only feed insects. They gave rise to amphibians of enormous size and diversity. Some resembled giant salamanders, others crocodile-like hunters lurking in the swamps. They laid their eggs in water, bound to moist environments. But within those wetlands, they were kings. Their diets included fish, insects, and smaller amphibians, and their presence echoed the first serious push of vertebrates onto land. Still, amphibians had limits. Their skins required moisture. Their eggs had no protective shells. They could not wander far from water. The Carboniferous would witness the first solution to this problem. Reptiles. Around 310 million years ago, certain amphibian-like creatures developed the amniotic egg, a marvel that could survive on land without drying out. This freed reptiles from the water's edge. They could spread into drier forests, uplands, and plains. Small, lizard-like at first, they carried within them the potential for dinosaurs, birds, and mammals. The Carboniferous giants did not last forever. As oxygen levels declined toward the period's end, their great size became unsustainable. By the Permian, arthropods had shrunk closer to the forms we know. But for millions of years, Earth was a stage for giants, flying, crawling, and slithering creatures that tested the limits of what life could be when the air itself was more generous. As the Carboniferous forests began to wane and oxygen levels drifted downward, the stage was set for a new chapter in Earth's unfolding drama. The Permian period, spanning from about 299 to 252 million years ago. This era was a bridge, a time when amphibians began to fade from dominance, reptiles surged into power, and the continents themselves inched toward one of the greatest unions in history, the formation of Pangea. The Permian world looked strikingly different from the lush swamps of the Carboniferous. The vast coal forests shrank as climates grew drier. Giant lycopods and horsetails that once towered over wetlands disappeared, leaving behind forests of conifers and seed ferns better adapted to arid conditions. Rivers cut across dusty plains, deserts spread across continental interiors, where the moderating influence of oceans could not reach. The once swampy earth was becoming a land of extremes. In this shifting environment, reptiles rose to power. Their amniotic eggs gave them freedom from water. No longer bound to swamps or ponds, they could colonize uplands, deserts, and wide-open plains. From small, lizard-like ancestors, reptiles diversified into astonishing forms. Some grew into hulking predators, others into stocky plant eaters, each claiming a niche in this new, harsher world. Among the most iconic of these early reptiles was Dimetrodon, a predator with a sail-like fin rising from its back. Though often mistaken for a dinosaur, Dimetrodon lived long before them. It was a synapsid, part of the lineage that would eventually give rise to mammals. Picture it stalking across Permian plains, its long jaws filled with sharp teeth, its sail possibly regulating body temperature in the shifting climates. On the herbivorous side stood creatures like Edaphosaurus, also bearing a great sail but feeding on plants instead of flesh. Stocky, lumbering, and armored with spines, it grazed on the hardy vegetation of the Permian landscape. Together, predators and prey established the first large-scale terrestrial ecosystems that resembled the predator-prey dynamics of later eras. Insects, too, adapted to the new conditions. The gigantic dragonflies and millipedes of the Carboniferous had vanished with falling oxygen levels, but smaller, more familiar forms thrived. Beetles diversified. Early relatives of cockroaches scuttled across leaf litter. The land buzzed with activity, though the giants were gone. Meanwhile, the continents themselves were drawing closer. Gondwana in the south, Laurasia in the north. Slowly, irresistibly, they moved toward collision. The closing of ancient oceans raised mountain belts like the Appalachians and the Urals, scars that remain today. With each collision, Earth's map grew simpler, converging toward the single, colossal supercontinent of Pangea. The world was shrinking into one great stage, yet beneath this apparent progress, disaster brewed. Massive volcanic eruptions in Siberia toward the end of the Permian released staggering amounts of carbon dioxide, tipping climate into chaos. Oceans warmed and stagnated, losing oxygen. Life on land and sea suffered. This slow-motion catastrophe would culminate in the Permian Triassic extinction event, the most devastating mass extinction in Earth's history, wiping out around 90% of species. The Permian was a time of grandeur and doom, of reptiles rising and ecosystems collapsing, of continents locking together to form Pangea. It was both a triumph of tectonics and a tragedy of life, proof that Earth's transformations always come at a cost. The slow march of continents, driven by the hidden engine of plate tectonics, reached a climax in the late Permian. For hundreds of millions of years, scattered lands had drifted across vast oceans, colliding, rifting, and drifting again. But by about 335 million years ago, a monumental union began, one that would reshape the entire planet, the assembly of Pangea. Imagine Earth as it was then. Gondwana, the mighty southern supercontinent, stretched across much of the globe, holding what would become South America, Africa, India, Antarctica, and Australia. To the north lay Laurasia, containing North America, Europe, and parts of Asia. Slowly, inexorably, these two giants drew closer, closing the oceans that once separated them. The Iapetus Ocean and the Rheic Ocean, teeming with marine life for hundreds of millions of years, disappeared as their floors were subducted beneath colliding continents. The collisions were titanic. Rock slammed against rock with forces beyond comprehension, raising mountain chains that still scar Earth's surface today. The Appalachians in eastern North America and the Urals in Russia are the long-faded remnants of those ancient collisions, monuments to a time when continents locked together in one grand embrace. By the early Permian, the process was complete. Nearly all of Earth's land had fused into one colossal supercontinent. Pangea stretched from the northern polar regions to the southern tip of Gondwana, nearly pole to pole. Its interior was so vast that much of it lay far from the sea, creating harsh climates unlike anything Earth had known before. Deserts the size of continents sprawled across its center. Winds swept over barren dunes. Rain rarely reached the interior, leaving plants and animals to adapt or perish in the arid extremes. But along the coasts, the story was different. Where seas still lapped against land, ecosystems flourished. Swamps and forests dotted the fringes. Amphibians lurked in wetlands. Reptiles spread across the plains, their eggs allowing them to thrive in environments where amphibians could not. The stage was set for reptiles to diversify and eventually give rise to the dinosaurs that would one day dominate this vast landmass. Surrounding Pangea was a single immense ocean, Panthalassa. Covering nearly 70% of Earth's surface, it was the largest ocean in history, dwarfing any body of water we know today. Its waves circled the globe uninterrupted, currents flowing for tens of thousands of miles. Within it swam early sharks, fish, and marine reptiles, adapting to the challenges of a world where one sea stretched almost endlessly. To the east of Pangea lay another important ocean, the Tethys Sea, nestled between Gondwana and smaller continental fragments. The Tethys would one day close, raising the Alps and Himalayas, but during Pangea's time it was a vital cradle of marine biodiversity. Coral reefs and ammonites thrived in its warm waters, creating ecosystems that would endure through much of the Mesozoic era. Pangea was more than geography. It was destiny. Its assembly reshaped climate, ecosystems, and evolution itself. It united creatures that had once been separated by oceans, allowing species to spread across vast ranges. But it also brought vulnerability. With land so concentrated, climate extremes became more severe, ecosystems more fragile. Pangea was a giant. But giants, as history shows, can fall hard. With the continents locked together into the vast expanse of Pangea, Earth entered a new chapter, one both magnificent and merciless. Life had already endured mass extinctions, shifting climates, and continents colliding, but now it faced the challenges of a supercontinent unlike any before. Pangea's size and position shaped everything: the air, the water, and the very creatures that crawled across its surface. The heart of Pangea was a land of extremes. Far from the oceans, rain struggled to reach its interior. Imagine deserts so vast they stretched for thousands of miles, their dunes rolling endlessly beneath scorching suns. Days were blisteringly hot, nights bitterly cold. Few plants could survive in such harshness. Scrubby conifers and drought-resistant ferns clung to the edges of life, while animals adapted to endure long stretches without water. Fossil evidence suggests that reptiles, with their scaly, water-retaining skin and protective eggs, flourished where amphibians faltered. Along Pangea's coasts, however, life thrived. Here, rivers spilled into the great Panthalastic Ocean, nourishing swamps and floodplains. In these fertile regions, ecosystems blossomed. Towering conifers formed forests. Seed ferns spread leafy canopies. Horsetails clustered near riversides, their segmented stalks rising like green pillars. Insects buzzed in the air. Beetles, dragonflies, and early relatives of cockroaches, reptiles patrolled the underbrush, some small and nimble, others large and imposing. Among the most striking of Pangea's creatures were the synapsids, the ancestors of mammals. One such giant was Dimetrodon, its long jaws lined with sharp teeth and a tall sail arching from its back. Though it looked reptilian, it belonged to a lineage closer to mammals than to dinosaurs. Dimetrodon hunted amphibians and smaller reptiles, its sail possibly helping it regulate body temperature in Pangea's fluctuating climates. Herbivorous synapsids also flourished. Edaphosaurus, with its stocky body and sail-covered back, grazed on tough Permian plants. Other plant eaters developed grinding teeth to process fibrous material, innovations that hinted at the mammalian chewing systems of the far future. These creatures dominated the landscapes long before dinosaurs rose to power. Amphibians, though challenged, still found niches in wetter regions. Some grew to enormous sizes, resembling crocodiles in both shape and lifestyle. They lurked in swamps, waiting to ambush prey that strayed too close to the water. But their reliance on moisture limited them. As the climate grew drier, reptiles claimed more territory, gradually overshadowing their amphibian cousins. The seas that lapped against Pangea were equally alive. The Tethys Sea, warm and shallow, hosted coral reefs, ammonites, and early marine reptiles. In Panthalassa, vast schools of fish swam alongside sharks that had already existed for hundreds of millions of years. The oceans carried nutrients and stability that the supercontinent's interior could not provide, becoming refuges of biodiversity during times of drought and climate stress. Life on Pangea was a paradox. It united ecosystems that had once been isolated, allowing species to spread widely. Yet its vast deserts and extreme climates also tested the limits of survival. It was a land of opportunity and struggle, where the resilient thrived and the fragile vanished. And looming over it all was an approaching storm, the end of the Permian, when volcanic fire and poisoned oceans would nearly erase life from the planet. As Pangea stood in its full majesty, stretching from pole to pole, deserts sprawling across its heart, seas encircling its edges, life seemed firmly rooted. Reptiles thrived. Synapsids ruled the plains. Amphibians lurked in swamps, and oceans teemed with fish, corals, and ammonites. Yet beneath this illusion of permanence, catastrophe brewed. The late Permian would deliver a cataclysm so severe that it nearly erased life from Earth altogether. Scientists call it the Permian-Triassic extinction event. Others simply call it the Great Dying. It began in fire. Around 252 million years ago, in what is now Siberia, volcanic eruptions of unimaginable scale tore through the crust. For nearly a million years, basaltic lava spilled from fissures, flooding an area larger than the United States. These eruptions released staggering amounts of carbon dioxide and methane, greenhouse gases that choked the atmosphere. At first, temperatures soared, oceans warmed, and life struggled to adapt. But the disaster did not stop with heat. The volcanic gases included sulfur dioxide, which dimmed the skies, causing acid rain to fall upon the land. Soils turned toxic, rivers grew acidic, and forests collapsed. The lush green world of Pangea began to wither. Plants withered, and with them the animals that depended on them. The oceans suffered most of all. As carbon dioxide poured into the air, it dissolved into seawater, acidifying the seas. Coral reefs, once vibrant ecosystems, crumbled. Warmer waters held less oxygen, leading to vast dead zones where marine creatures suffocated. Methane released from seafloor hydrates may have triggered runaway warming, amplifying the catastrophe. The toll was staggering. An estimated 90% of marine species vanished. Trilobites, survivors of nearly 300 million years, disappeared forever. Coral reefs collapsed and would not return for millions of years. On land, around 70% of vertebrate species perished. Synapsids like Dimetrodon gave way to new lineages. Insects, previously resilient, suffered their only known mass extinction. Forests fell silent. Imagine walking across Pangea during those years. The air would be heavy, hot, and suffocating. Ash might drift from the sky. The once bustling swamps would be empty. Rivers would run sluggish and acidic. Carcasses would litter the ground. Even the oceans, normally a refuge, would be strangely quiet, their vibrant life replaced by silence and stench. And yet, even in this darkest hour, life endured. A few hardy species survived. Small reptiles, burrowing animals, certain fish, and microbial communities in shallow seas. These survivors carried the torch of evolution through the darkness, setting the stage for recovery in the Triassic. Out of near annihilation would rise new creatures, new ecosystems, and ultimately, the dinosaurs. The Great Dying is a reminder of Earth's fragility. It shows how interconnected land, sea, and sky truly are, and how swiftly stability can collapse when the balance is broken. It was the closest Earth has ever come to becoming a barren world. That it recovered at all is a miracle written in stone. The Great Dying left Earth scarred and silent. Forests had collapsed, oceans stagnated, and the air itself bore the weight of volcanic poisons. But life, though broken, was not extinguished. Slowly, cautiously, the survivors of the Permian-Triassic extinction began to rebuild the tapestry of existence. This was the dawn of the Triassic period, a time of rebirth, innovation, and the first steps toward the age of dinosaurs. At first, the landscapes of Pangea were barren. Deserts sprawled across the supercontinent's vast interior. Vegetation was sparse, dominated by hardy conifers and seed ferns clinging to the edges of rivers and coasts. Gone were the lush swamp forests of the Carboniferous, and gone too were the sprawling herds of great synapsids. What remained were scattered survivors, small reptiles, burrowing animals, amphibians in damp refuges, and resilient plants that could endure arid conditions. From these survivors came new beginnings. Reptiles diversified quickly, filling the empty niches left by extinction. Some grew into archosaurs, a group that would eventually give rise to both crocodiles and dinosaurs. At first, they were modest in size, slender, agile hunters darting across dry plains, but evolution was restless. Within a few million years, archosaurs split into two dominant paths: the crocodile-line archosaurs, which would adapt to semi-aquatic lifestyles, and the dinosaur-line archosaurs, which would one day rule the land. Meanwhile, another lineage was quietly preparing for greatness: the mammal-like reptiles, or therapsids. Though many had perished in the Great Dying, a few small forms endured. Over time, they became more efficient, with differentiated teeth and more advanced jaws, traits that foreshadowed mammals. In the Triassic, they were modest, rat-sized insectivores, perhaps burrowers, but they carried within them the seeds of the warm-blooded creatures that would one day dominate after the dinosaurs. The oceans, too, began their recovery. Coral reefs were gone, but other ecosystems emerged. Ammonites and early mollusks spread through the seas. Fish diversified again, and soon the oceans saw the rise of new marine reptiles. Ichthyosaurs, sleek and dolphin-like, darted through Panthalassa's vast waters, while nothosaurs paddled along shallow coasts. Life had found ways to adapt, reshaping itself into new forms. By the Middle Triassic, Earth was vibrant again. Conifer forests thickened. Rivers and floodplains supported ecosystems of insects, amphibians, and reptiles. Archosaurs grew larger and more diverse. Some, like Postosuchus, became apex predators, towering over the landscape with crocodile-like jaws and powerful limbs. Others remained small, But evolution was quietly experimenting, refining body plans that would culminate in dinosaurs. And indeed, by the late Triassic, the first true dinosaurs appeared. They were not yet the giants of legend, but swift, two-legged hunters like Coelophysis. Lightweight, agile, and quick to reproduce, they had advantages that would carry them far. Alongside them, the first primitive mammals emerged, tiny, shrew-like creatures scurrying in the underbrush, largely unnoticed by the reptilian giants that shared their world. The Triassic was a time of resilience. From the ashes of near-total annihilation, Earth had built something new. Life had not simply returned, it had reinvented itself, setting the stage for one of the most extraordinary chapters in natural history, the rise of the dinosaurs. By the late Triassic, roughly 230 million years ago, Pangea was alive again. Forests of conifers spread along river valleys, seed ferns carpeted the ground, and the air buzzed with insects. Reptiles of every shape and size prowled the land, from crocodile-like archosaurs to lumbering herbivores. Yet amid this crowded stage, a new group of creatures was quietly stepping into the spotlight. Creatures that would one day dominate Earth for over 160 million years. These were the dinosaurs. At first, dinosaurs were not the giants we often imagine. They were small, nimble, two-legged hunters, more like swift lizards than towering monsters. Eoraptor, one of the earliest known dinosaurs, was scarcely the size of a dog. It darted through Triassic undergrowth, chasing insects and small reptiles. Herrerasaurus, a larger predator, reached lengths of 3 meters, hunting with sharp teeth and clawed hands. These early dinosaurs were light, fast, and opportunistic, traits that gave them an edge in a world still recovering from catastrophe. What made dinosaurs different from other reptiles was not size but design. Their legs were positioned directly beneath their bodies, unlike the sprawling limbs of crocodile-like archosaurs. This upright posture gave them efficiency, allowing them to run longer and faster. Their lightweight skeletons, often with hollow bones, reduced weight without sacrificing strength. Some may even have had feathers or feather-like coverings, adaptations that would later give rise to flight. At the same time, herbivorous dinosaurs were beginning to appear. Early sauropodomorphs like Plateosaurus grew large by Triassic standards, reaching lengths of 9 meters. They walked on 2 legs or 4, using long necks to graze on vegetation others could not reach. Though not yet the towering giants of the Jurassic, these were the ancestors of the colossal sauropods to come. Dinosaurs did not yet rule the Earth. They shared Pangea with many rivals, massive crocodile-like predators such as Postosuchus, armored herbivores like etiosaurs, and early mammals scurrying in the shadows. But they were survivors in a changing world. The Triassic climate was harsh, marked by droughts and seasonal extremes. Dinosaurs' efficient breathing systems, upright posture, and rapid growth rates may have allowed them to thrive where others struggled. Meanwhile, the oceans told their own story of evolution. Ichthyosaurs swam like dolphins through Panthalassa, while long-necked nothosaurs prowled shallow seas. Plesiosaurs were on the horizon, soon to dominate marine environments. In the skies, the first true flyers appeared, the pterosaurs, relatives of dinosaurs that stretched leathery wings and soared above coasts and rivers. The Triassic was a world of experimentation, with reptiles pushing into every possible niche. Then, another crisis struck. Around 201 million years ago, near the end of the Triassic, massive volcanic eruptions associated with the opening of the Atlantic Ocean triggered climate chaos. Many large archosaurs, amphibians, and marine reptiles perished in this extinction event. Dinosaurs, however, survived, and with their competitors gone, they seized the opportunity. From small, swift hunters and lanky grazers, dinosaurs would expand into an astonishing variety of forms. In the Jurassic and Cretaceous, they would grow into giants, take to the skies, and dominate ecosystems on every continent. But here, in the late Triassic, their story was only beginning, a quiet dawn before a long and glorious reign. The Triassic had ended in fire and ash, with volcanic eruptions reshaping climates and clearing the stage of many rivals. From that chaos, the Jurassic dawned around 201 million years ago, and with it came the true ascendance of dinosaurs. What had once been small, agile survivors now blossomed into a dazzling array of forms, some graceful, some ferocious, and some so colossal that they still inspire awe today. In the early Jurassic, the world was warming again. The supercontinent Pangea still held together, but cracks were beginning to appear. Rift valleys opened as the first hints of the Atlantic Ocean formed. Forests of conifers, cycads, and ginkgos spread across fertile lowlands. Ferns blanketed the understory. Rivers meandered through broad floodplains. This was a world rich in vegetation, fuel for giants. Among the first of these giants were the sauropodomorphs, the ancestors of the largest creatures ever to walk on land. Plateosaurus, already impressive in the late Triassic, gave way to true sauropods, towering, long-necked plant-eaters that could strip trees of their foliage in minutes. Creatures like Volcanodon and Barapasaurus stretched up to 15 meters long, their massive bodies supported by pillar-like legs. They gathered in herds, their necks swaying high above the ground as they grazed on treetops unreachable to other animals. But no ecosystem is complete without predators. The early Jurassic saw the rise of formidable hunters such as Dilophosaurus, with its twin crests and sharp teeth. Lean and agile, it roamed floodplains in search of prey, perhaps hunting in packs. Later, larger predators emerged, ancestors of the allosaurs and tyrannosaurs yet to come. The balance of power between hunter and hunted drove evolution forward, shaping stronger defenses and sharper weapons on both sides. Meanwhile, in the skies, the pterosaurs perfected flight. These leathery winged reptiles soared along coastlines and rivers, some no larger than sparrows, others with wingspans rivaling small planes. They were the first vertebrates to conquer the air, millions of years before birds would evolve. Their presence added a new dimension to Jurassic life. Creatures could now dominate land, sea, and sky. The oceans themselves brimmed with new marvels. Sleek ichthyosaurs raced through Panthalassa's waters, hunting fish and squid with the speed of modern dolphins. Long-necked plesiosaurs cruised the shallows, their four paddle-like limbs propelling them gracefully. Predatory pliosaurs with massive jaws became apex hunters of the seas. Coral reefs reappeared, buzzing with life, rebuilding ecosystems destroyed in earlier extinctions. For mammals, the Jurassic was a quiet age. Small, shrew-like creatures scurried in the underbrush, mostly nocturnal, feeding on insects and seeds. They remained in the shadows, overshadowed by the dominance of dinosaurs. But their story was far from over. They would bide their time in the dark, waiting for their chance to rise. The Jurassic was not just a time of survival, it was a time of splendor. From towering sauropods casting long shadows across valleys, to predators roaring under alien skies, to flying reptiles circling above, Earth had become a stage of giants. Pangea's slow breakup created new habitats, new climates, and new opportunities, fueling the explosion of diversity that defined this age. The reign of dinosaurs had begun in earnest, and it was only the beginning of their golden era. By the middle of the Jurassic, around 170 million years ago, the supercontinent Pangea had begun to fracture. What was once one colossal landmass, stretching nearly from pole to pole, now cracked and split under the slow but relentless pull of tectonic forces. This breakup reshaped Earth's geography, altered climates, and opened doors for life to diversify in ways that would define the Mesozoic era. The first great rift appeared between what would become North America and Africa. Magma surged upward, creating volcanic landscapes and rift valleys that would eventually give birth to the Atlantic Ocean. Though narrow and shallow at first, this newborn ocean widened with each passing million years, severing connections that had bound ecosystems together. Where once animals could roam freely across Pangea, the widening seas began to isolate populations, setting the stage for evolutionary divergence. As continents drifted apart, climates shifted. The vast deserts of Pangea's interior, where rain had seldom reached, gave way to more varied environments. Coastal regions expanded, creating fertile floodplains, wetlands, and forests. Rainfall increased in some areas, allowing lush jungles to thrive. Other regions dried further, producing arid savannas and scrublands. Diversity in landscapes meant diversity in life. Species that once competed directly now found new ecological niches in their separated worlds. The seas transformed as well. The global ocean Panthalassa still dominated, but now it was joined by widening seaways. The Tethys Ocean, stretching across the equator, became a hotspot of marine biodiversity. Its warm, shallow waters nurtured coral reefs, ammonites, and marine reptiles. With more coastlines to explore, ichthyosaurs and plesiosaurs flourished, while predators like pliosaurs grew massive, ruling the depths with jaws built for crushing prey. On land, the breakup of Pangea fueled an evolutionary explosion. Sauropods, freed to spread into new regions, grew ever larger. By the late Jurassic, giants like Brachiosaurus and Diplodocus towered over forests, reaching lengths of 25 meters or more. Herds of these titans roamed floodplains, their long necks sweeping across canopies like living cranes. Predators adapted in response. Allosaurus, the apex hunter of the Jurassic, grew to over 9 meters, armed with serrated teeth designed for slicing flesh. Agile and deadly, it stalked the same floodplains as the sauropods, striking down the young, the weak, or the unwary. Smaller predators like Ceratosaurus and Dilophosaurus hunted in different niches, ensuring no meal was left unclaimed. Meanwhile, the skies flourished with pterosaurs. Insects buzzed across flowering ferns, and above them soared leathery-winged hunters. Some grew massive, while others specialized in darting after fish or plucking prey from the ground. The skies, once empty, now teemed with movement. The breakup of Pangea did more than reshape landscapes. It fueled isolation, and isolation drives evolution. Populations cut off from each other began to develop unique traits. In time, this would lead to extraordinary diversity. Unique dinosaurs in different regions, distinct marine reptiles in separate oceans, and eventually, entirely new forms of life that would never have existed had Pangea remained whole. The slow tearing of Pangea was not destruction, it was creation. By breaking apart, it transformed Earth into a mosaic of worlds, each with its own climates, its own challenges, its own evolutionary stories. By the late Jurassic, around 150 million years ago, Earth had become a patchwork of new worlds. The supercontinent Pangea was no longer whole. Its rifts had widened into oceans, its deserts had broken into fertile plains, and its climates had diversified. Across this transformed landscape, dinosaurs reached new heights of diversity, and some reached sizes that defy imagination. This was the age of giants, when Earth's stage was ruled by creatures unlike anything before or since. The most spectacular of these were the sauropods. Herds of Diplodocus stretched their impossibly long necks into treetops, sweeping leaves in wide arcs. Brachiosaurus, with front legs longer than its hind legs, stood like a living tower, its head rising as high as a 4-story building, its weight rivaling dozens of elephants. Their size was not just impressive, it was a strategy. Massive bodies deterred predators, digested tough plants efficiently, and allowed these giants to reach food sources far beyond the grasp of smaller creatures. The very sight of a herd moving across the floodplain must have been breathtaking. An undulating line of necks, tails swinging like living whips, the ground trembling under their colossal weight. But the giants did not rule unchallenged. Apex predators prowled among them, keeping balance in the ecosystem. Chief among them was Allosaurus, the terror of the late Jurassic. Growing up to 9 meters long, with powerful jaws and serrated teeth, it hunted in packs or alone, using ambush and strategy to bring down prey. Evidence from fossilized bite marks suggests that Allosaurus did not hesitate to attack even massive sauropods, targeting the young, the sick, or the isolated. Other predators filled specialized roles. Ceratosaurus, with its horned snout, stalked wetter environments, preying on fish and smaller dinosaurs. Torvosaurus, another large theropod, rivaled Allosaurus in size and strength, ensuring constant competition among hunters. This was not a peaceful age. It was a dynamic balance of giants and killers, survival and adaptation. Amid this drama, smaller dinosaurs thrived too. Stegosaurus, one of the most iconic of all, lumbered through Jurassic forests with its double row of bony plates and spiked tail, the fearsome Thagomizer. Though a plant eater, it was no easy target. Its tail spikes could pierce predators, a reminder that even gentle grazers had defenses in a world of giants. Ornithopods, nimble herbivores, scurried in herds, using speed and coordination to evade predators. The oceans were no less dramatic. Pliosaurus, a marine reptile with jaws longer than a man is tall, dominated the seas. Ichthyosaurs, dolphin-like reptiles, hunted schools of fish with streamlined grace. Long-necked plesiosaurs glided through shallows, their bodies propelled by 4 powerful paddles. The seas were as alive with monsters as the land. Above, the skies filled with pterosaurs. Some, like Rhamphorhynchus, skimmed fish from waves with long, toothy beaks. Others soared on wingspans stretching meters across, masters of the Jurassic air. Though birds were only just beginning their story, the skies were already alive with reptilian flight. The late Jurassic was an age of abundance, diversity, and grandeur. Dinosaurs had grown into forms so immense they seemed like moving mountains. Predators tested their strength against impossible odds. Forests and plains echoed with life on a scale unmatched in Earth's history. It was an age when Earth truly belonged to giants. The Jurassic giants had reigned supreme, but as Earth shifted into the early Cretaceous around 145 million years ago, change was in the air and in the soil. The world was no longer dominated solely by towering conifers, cycads, and ferns. Something extraordinary began to take root: flowering plants. With their blossoms, fruits, and seeds, they reshaped ecosystems in ways that would ripple through every corner of life. At first, these flowering plants, angiosperms, were modest, small shrubs with delicate blooms. They competed quietly against the well-established conifers and seed ferns. But flowers carried powerful advantages. Their enclosed seeds offered better protection. Their blossoms attracted pollinators, early insects that unknowingly spread pollen from one bloom to another. This partnership between plants and insects triggered a cascade of evolutionary innovation. What began as subtle blossoms would eventually cover the world in color, fragrance, and diversity. Insects themselves were changing alongside these plants. Early bees, beetles, and butterflies began to appear, drawn to the nectar and pollen that flowers provided. Their buzzing activity was the start of a new rhythm in nature, the intricate dance of pollination. With insects and flowers working together, plants spread faster, more efficiently, and into new environments. This silent revolution would come to transform Earth's landscapes forever. Meanwhile, the dinosaurs adapted to this new world. Herbivores found new sources of food, while predators adjusted to changing prey. Among the plant eaters, iguanodonts thrived. These large ornithopods grazed in herds, walking on all fours, but capable of rearing up on hind legs to reach higher branches. Their thumb spikes were powerful weapons, deterring predators. Agile, intelligent, and social, iguanodonts foreshadowed the hadrosaurs, the duck-billed dinosaurs, that would later dominate the Cretaceous. Predators, too, were evolving. Sleek hunters like Neovenator and Acrocanthosaurus stalked floodplains, their sharp senses and powerful jaws making them formidable threats. Crocodile-line reptiles lurked in rivers, ambushing anything that came too close to the water's edge. This was a world where survival depended on adaptation, and evolution responded with creativity. Sauropods, the colossal plant eaters of the Jurassic, remained, though their dominance waned in many regions. Some groups, like the titanosaurs, began to rise, destined to become the largest land animals in history. They adapted to shifting climates and vegetation, spreading across southern continents with incredible success. The oceans flourished with their own dramas. Plesiosaurs and pliosaurs continued to rule, while ichthyosaurs reached their peak before beginning a slow decline. Ammonites spiraled in countless forms, their shells glittering beneath the waves. New marine reptiles appeared, including the ancestors of the mosasaurs that would dominate later in the Cretaceous. The seas, warmed by shifting currents, supported ecosystems as rich and deadly as those on land. Above it all, the skies changed too. Pterosaurs grew larger and more specialized. Some skimmed fish from the ocean surface, while others hunted inland. And quietly, almost invisibly, the first true birds, descendants of small feathered dinosaurs, spread their wings. With feathers, hollow bones, and flight, they marked the beginning of an entirely new story. The early Cretaceous was an age of transition. Giants still roamed, but new players were rising. Flowers were blooming, insects were dancing, and the foundations of modern ecosystems were being laid. It was the world's first glimpse of the vibrant, colorful planet we know today. By the late Cretaceous, around 100 to 66 million years ago, Earth had become a patchwork of continents that looked far more like the world we know today. The breakup of Pangea was nearly complete. North America had drifted away from Europe and Africa. South America was separating from Africa. India was racing northward, destined to one day collide with Asia. This fragmentation reshaped climates, created isolated ecosystems, and fueled a final burst of evolutionary creativity. Life was at its peak, dazzling in variety and scale. On land, the dinosaurs reached their greatest diversity. In the northern continents, the tyrannosaurs rose to power. Early relatives were modest in size, but by the end of the Cretaceous, evolution had produced Tyrannosaurus rex, a predator so iconic it still captures imaginations today. Standing over 12 meters long, with jaws capable of crushing bone, T-Rex was not only a hunter, but also a scavenger, dominating ecosystems with raw power. But the herbivores of the late Cretaceous were no less extraordinary. Herds of hadrosaurs, the duck-billed dinosaurs, grazed across floodplains, their hollow crests producing resonant calls that may have echoed like horns across the land. Some, like Parasaurolophus, had elaborate head crests that might have been used for communication, display, or both. Their social behavior, complex for herbivores, painted a picture of herds more akin to wildebeest or elephants than simple grazers. Elsewhere, ceratopsians, the horned dinosaurs, flourished. Triceratops, with its 3 horns and massive frill, became one of the most famous. Herds of these armored giants likely defended themselves from predators with both horns and sheer numbers. Their diversity was staggering, with countless species evolving unique frills and horn arrangements, perhaps as a form of display in mating rituals or species recognition. And then there were the titanosaurs, the last great sauropods. Unlike their Jurassic cousins, these long-necked giants adapted to the warmer, more fragmented Cretaceous world. They spread across South America, Africa, and Asia, some reaching lengths of over 30 meters. Argentinosaurus and Patagotitan were among the largest creatures ever to walk the earth. Living mountains that grazed on forests of angiosperms and conifers. The oceans of the late Cretaceous were no less fierce. The mosasaurs, marine reptiles related to modern lizards, became the undisputed rulers of the seas. With sleek, elongated bodies and double-hinged jaws, they grew to lengths of 15 meters or more, preying on fish, turtles, and even other mosasaurs. Sharks thrived too, with forms that closely resemble many species we see today. Ammonites spiraled in endless diversity, their shells glittering across shallow seas, while sea turtles and marine birds joined the competition for survival. Above the land and seas, the skies were filled with giants. Pterosaurs reached their zenith, with Quetzalcoatlus spreading wings nearly 10 meters across, one of the largest flying creatures in history. Birds, descended from small feathered dinosaurs, diversified as well, their forms foreshadowing the avian world that would rise after the dinosaurs' fall. The late Cretaceous was Earth's last golden age of dinosaurs. The continents were alive with thunderous herds, the seas churned with marine monsters, and the skies stretched wide with flyers. Life seemed unstoppable, flourishing in every corner of the globe. Yet beyond the horizon, fate was preparing its final blow, an event that would end this age of wonder in a single devastating instant. For millions of years, the late Cretaceous world flourished. Herds of hadrosaurs roamed fertile floodplains. Triceratops locked horns in dramatic displays. Tyrannosaurs prowled as apex predators, their bone-crushing jaws ensuring dominance. In the oceans, mosasaurs and sharks ruled, while in the skies, pterosaurs soared alongside the first true birds. It was a vibrant, thriving world, a golden age. But around 66 million years ago, in a single day, everything changed. The story begins in space. A massive asteroid, more than 10 kilometers wide, hurtled toward Earth at tens of thousands of miles per hour. For countless millennia, it had drifted silently through the solar system, unnoticed. Then, in a moment of cosmic chance, its trajectory aligned with Earth's orbit. On that fateful day, it struck near the Yucatan Peninsula of present-day Mexico, slamming into shallow seas and releasing energy equal to billions of atomic bombs. The impact was instantaneous devastation. Shockwaves rippled outward, flattening forests for thousands of miles. Tsunamis taller than skyscrapers surged across coastlines. The atmosphere ignited as molten debris rained down, setting wildfires on a global scale. Within hours, much of Earth was aflame, but the deadliest effects unfolded in the days and years that followed. Dust, soot, and vaporized rock filled the sky, forming a thick shroud that blocked sunlight. Darkness fell over the planet, lasting weeks, then months. Photosynthesis collapsed. Plants withered. Food chains broke apart from the bottom up. Herbivores starved, and predators soon followed. Temperatures plummeted in a global winter, then spiked as greenhouse gases from burning forests and vaporized rock flooded the atmosphere. The climate swung wildly between extremes, leaving ecosystems unable to recover. Acid rain poisoned soils and seas, while oceans became more acidic, devastating marine life. In this chaos, the great dynasties of the Mesozoic vanished. Non-avian dinosaurs, once masters of the land, perished. The mighty T-Rex, the colossal titanosaurs, the horned triceratops, all gone. In the seas, ammonites, mosasaurs, and countless marine reptiles disappeared. Pterosaurs, rulers of the skies for over 150 million years, vanished forever. Nearly 75% of Earth's species were lost. And yet, as in every extinction before, life found a way. Small mammals, some no bigger than rats, survived in burrows and niches. Birds, the last living dinosaurs, endured, feeding on seeds and insects. Crocodiles, turtles, and certain amphibians made it through, sheltered in waterways. Even in the darkest hour, resilience flickered. The asteroid did not end life. It ended an age. The dinosaurs' reign, spanning more than 160 million years, had come to a close. In their absence, survivors would rise to claim the Earth. Forests would regrow, oceans would refill with new forms, and mammals, long overshadowed, would step into the light. The cataclysm was both an ending and a beginning. It reminds us of the fragility of life, the power of chance, and the resilience of the planet itself. The world that emerged after would never again belong to the dinosaurs. It would belong to the creatures that had once cowered in their shadows, creatures that would one day give rise to us. In the silence that followed the asteroid's impact, Earth was a wounded world. Forests lay in ashes, oceans were cloudy with debris, and the great giants of the Mesozoic were gone. Yet slowly, life began to creep back. The Paleogene period, beginning around 66 million years ago, was the dawn of a new era. With the dinosaurs gone, the stage was clear for a different cast of creatures to rise, the mammals. For over 160 million years, mammals had lived in the shadows. They were small, nocturnal, and often overlooked, scurrying through underbrush, burrowing underground, or hunting insects by night. But survival had honed their resilience. Many could hide in burrows, eat a wide variety of foods, and reproduce quickly. These traits allowed them to endure the cataclysm that killed the dinosaurs. When the skies cleared and forests regrew, mammals were ready to seize the opportunities left behind. At first, the mammals of the Paleogene were modest. Small insectivores and rodent-like creatures scurried across the recovering landscapes. But with predators like tyrannosaurs gone and giant herbivores like hadrosaurs vanished, new ecological niches lay open. Evolution, relentless and creative, began to fill them. Some mammals grew larger, becoming the first true grazers and browsers. Others took to the trees, evolving into early primates with grasping hands and stereoscopic vision. Still others returned to the water, beginning the transformation that would one day produce whales. Within just a few million years, mammals had spread into every environment: forests, grasslands, rivers, and seas. Birds, too, flourished in the Paleogene. Descended from the dinosaurs that had survived, they diversified into forms familiar to us today: waterfowl, songbirds, raptors, and ground dwellers. With wings, feathers, and beaks adapted to countless niches, they carried forward the legacy of their dinosaur ancestors. Insects rebounded as well, partnering with flowering plants to continue the silent symphony of pollination that had begun in the Cretaceous. The Earth itself changed dramatically during the Paleogene. With continents drifting apart, new oceans widened and new climates emerged. India raced northward and would soon collide with Asia, raising the Himalayas. South America drifted into isolation, becoming a crucible for unique species. The Atlantic Ocean grew, separating Europe and North America, while Antarctica began to freeze at its southern pole. These tectonic shifts shaped habitats, climates, and the evolutionary pathways of the animals that inhabited them. Forests dominated much of the Paleogene world, warm and lush. Early horses, no larger than foxes, picked their way through the undergrowth. Strange hoofed mammals, ancestors of elephants and rhinos, wandered in small herds. Predatory mammals evolved sharper teeth and swifter bodies to chase their prey. For the first time in history, mammals, not reptiles, were the undisputed rulers of the land. The Paleogene was not only about survival, it was about innovation. Mammals experimented with size, shape, and lifestyle. Some grew larger than any mammal before them, while others refined intelligence and social behavior. The groundwork was being laid for future titans: elephants, whales, great cats, and eventually humans. The asteroid had ended one dynasty, but it had cleared the way for another. From the ashes of the dinosaurs' world, the age of mammals had begun. By the time Earth entered the Neogene period, about 23 million years ago, the planet had transformed yet again. The once dominant forests began to thin in many regions, replaced by sprawling grasslands. This quiet revolution in vegetation reshaped the course of evolution, driving mammals into astonishing new forms and setting the stage for the Ice Age giants that would follow. Grasses had existed for millions of years, but in the Neogene they spread across continents, covering vast plains. Unlike trees, grasses could regrow quickly after being grazed, making them resilient to the appetites of herbivores. Their roots formed tough sods that stabilized soils and reshaped river systems. This new environment favored animals that could run fast across open ground, digest tough plants, and see far into the distance. Herds of grazing mammals flourished. Early horses, once small forest dwellers, evolved into larger, fleet-footed runners with high-crowned teeth built to grind grass. Antelope, camels, and bison spread across plains, forming vast herds. In South America, unique groups like litopterns and notungulates filled similar roles. Africa's grasslands gave rise to familiar icons: zebras, wildebeest, and giraffes. Wherever grasslands spread, herds followed, reshaping ecosystems with their migrations. Predators adapted in parallel. The Neogene saw the rise of swift hunters like cheetah-like cats, hyenas, and canids that specialized in chasing prey across open savannas. Saber-toothed cats with their long, curved fangs became formidable ambush predators. Packs of early wolves and wild dogs developed strategies of endurance, hunting by exhausting prey in long pursuits. This was an era of arms races, speed against speed, strength against cunning. But the most awe-inspiring of the Neogene mammals were the giants. Proboscideans, ancestors of modern elephants, grew to staggering sizes. Dinotherium, with downward curving tusks, browsed in forests and plains alike. Some reached heights of over 4 meters at the shoulder. In South America, Megatherium, the giant ground sloth, lumbered through woodlands, standing nearly as tall as a giraffe when it reared on its hind legs. In Eurasia, towering rhinoceroses like Paraceratherium, one of the largest land mammals ever, browsed treetops with necks longer than most modern giraffes. Meanwhile, the seas swelled with their own leviathans. Whales, having returned fully to aquatic life millions of years earlier, diversified into forms we would recognize today. Baleen whales filtered plankton from the seas, while sperm whales hunted giant squid in the deep. Sharks reached record sizes, none more terrifying than Megalodon, a predator that may have grown up to 18 meters long, its jaws wide enough to swallow a car. The Neogene oceans were theaters of power and scale. The Earth's surface itself was shifting dramatically. Continents continued to drift, altering climates. The collision of India and Asia thrust the Himalayas skyward, reshaping global weather. The closure of seaways redirected ocean currents, cooling the planet and beginning the long descent into the Ice Age. Grasslands expanded, forests retreated, and the creatures of the Neogene adapted or vanished. The Neogene was a world of innovation, resilience, and grandeur. It was here that ecosystems began to look strikingly modern. Herds on the plains, predators in pursuit, oceans alive with whales and sharks. Yet looming ahead was the Ice Age, when climates would swing violently, glaciers would advance, and survival would demand even greater ingenuity. As Earth crossed into the Quaternary period, beginning about 2.6 million years ago, the climate grew harsher, wilder, and more unpredictable. The planet entered a cycle of ice ages, when glaciers advanced and retreated over continents like great grinding waves of ice. This frozen rhythm reshaped landscapes, carved valleys, and tested every living thing with extremes of cold and scarcity. Yet out of this crucible of ice and struggle came some of the most iconic creatures in Earth's history, and, at last, the rise of humanity. Imagine the world then. Vast sheets of ice stretching across North America, Europe, and Asia, kilometers thick. Glaciers carved fjords into Scandinavia and gouged out the Great Lakes of North America. Sea levels dropped as water froze into ice, exposing land bridges that connected continents. During these glacial periods, herds of animals roamed across new paths, and predators followed in their wake. When the ice retreated, forests reclaimed the land, only for the cycle to begin again tens of thousands of years later. Among the titans of the Ice Age were the mammoths. These massive relatives of elephants, covered in shaggy fur and equipped with long, curved tusks, grazed on the frozen steppes. Some species, like the woolly mammoth, became icons of resilience, surviving bitter winds and endless winters by huddling in herds and foraging beneath snow for grasses. Alongside them wandered mastodons, shorter and stockier cousins with teeth adapted to browsing shrubs and trees. Predators, too, grew formidable. The saber-toothed cats, like Smilodon, stalked the plains with fangs longer than a man's hand, built for delivering killing blows to thick-skinned prey. Packs of dire wolves hunted cooperatively, their bones preserved in places like the La Brea tar pits, where countless Ice Age animals became trapped. Giant short-faced bears towered over modern grizzlies, their sheer size making them apex scavengers and hunters. The Ice Ages also nurtured giants beyond the familiar. Megatherium, the giant ground sloth of South America, lumbered like a living fortress. Glyptodon, a massive, armored mammal resembling a Volkswagen-sized armadillo, trundled across grasslands. Herds of giant bison, horses, and antelope-like creatures thrived in the cold, adapted steppes. It was a world of abundance, but one finely tuned to the rhythms of ice. And then, into this stage stepped humans. Early hominins had already been evolving in Africa during the warmer intervals of the Pliocene. But during the Quaternary, Homo erectus, and later Homo sapiens, spread across the globe. They followed herds across grasslands, crossed land bridges into new continents, and braved glacial winters with fire, clothing, and ingenuity. Unlike other animals, humans adapted not just with bodies, but with minds, tools, language, and culture. For tens of thousands of years, humans lived alongside the giants of the Ice Age. They hunted mammoths, painted their likeness on cave walls, and told stories around fires while saber-toothed cats roared beyond the light. The Ice Age was not just nature's trial, it was humanity's forge. Out of it came the species that would one day reshape the planet itself. The Quaternary reminds us that even in the harshest conditions, life finds a way. The glaciers advanced and retreated, giants rose and fell, and a fragile new species took its first steps toward dominance. Around 12,000 years ago, the last great ice age began to loosen its grip on Earth. Glaciers that had once stretched across continents melted back, releasing torrents of water that carved rivers and raised sea levels. Forests crept northward, reclaiming tundra and steppe. The world was warming, reshaping itself into the landscapes we recognize today. But with this transformation came profound loss, the twilight of the Ice Age megafauna, the mammoths, saber-toothed cats, and countless other giants that had ruled for millennia. The great herds of woolly mammoths, which had thundered across Eurasia and North America, dwindled as their icy grasslands shrank. Some small populations lingered on remote islands like Wrangel Island in the Arctic, surviving thousands of years longer than their mainland kin, but eventually even they disappeared. The mastodons, forest browsers with stocky builds, vanished as changing climates and human hunters took their toll. Predators, too, faded. The fearsome saber-toothed cat, Smilodon, with its iconic fangs, disappeared from the Americas. The dire wolves, once apex hunters in packs across the plains, were gone. The giant short-faced bear, taller than any modern bear when standing upright, vanished into extinction. In South America, armored giants like glyptodons, as large as cars, disappeared, as did the massive ground sloths like Megatherium. Within a geological blink, the rich bestiary of the Ice Age collapsed. Why did these giants fall? Scientists believe it was a combination of two forces: climate change and human expansion. As the world warmed, the icy steppes and tundras that supported many megafauna gave way to forests and wetlands. Habitats shrank and food sources shifted. At the same time, humans, ingenious, adaptable hunters, spread rapidly across continents. With fire, weapons, and coordinated strategies, they could bring down even the largest beasts. Archaeological sites show mammoth bones with cut marks, camps littered with the remains of hunted giants. It was not climate alone, nor humans alone, but the combined pressures that pushed these species to the edge. For early humans, this was both tragedy and opportunity. The loss of megafauna forced communities to innovate, turning to smaller game, fishing, and eventually agriculture. Yet before they vanished, the great animals of the Ice Age had left their mark on human culture. Cave paintings in Lascaux and Chauvet immortalized mammoths, bison, and lions. Stories told around fires surely echoed with respect, fear, and reverence for the giants that shared the land. These creatures were not only food and danger, they were symbols woven into humanity's earliest myths. As the Ice Age ended, humans began to settle, cultivate crops, and domesticate animals. Rivers like the Nile, Tigris, and Euphrates became cradles of civilization. The extinction of the megafauna marked the close of one era and the opening of another, the age of human dominance. Yet the memory of the Ice Age giants lingers, etched into bones buried in tar pits, painted on cavern walls, and carried in our imagination as we wonder what it must have been like to stand in their shadow. The end of the Ice Age was not just a passing of species. It was a turning point in Earth's story, when nature's giants gave way to the rise of humankind. With the Ice Age ended and glaciers retreating, Earth entered the Holocene epoch, about 11,700 years ago, the epoch we still live in today. It was a time of profound change, not because of tectonic shifts or asteroid impacts, but because of the rise of a single species, humankind. What began as scattered bands of hunter-gatherers soon blossomed into civilizations that would reshape landscapes, ecosystems, and even the climate itself. The warming climate created fertile valleys and predictable seasons, offering humans something the Ice Age could not: stability. In regions like the Fertile Crescent, between the Tigris and Euphrates rivers, people began experimenting with planting seeds and tending crops. Wheat and barley became the first cultivated grains. Goats, sheep, and cattle were domesticated, providing milk, meat, and companionship. This shift from foraging to farming was revolutionary. It anchored humans to the land, giving rise to villages, then cities, then empires. Agriculture spread outward like ripples in a pond. Rice paddies flourished in the valleys of China. Maize became the backbone of societies in the Americas. Millet and sorghum took root in Africa. With each harvest, populations grew, and with growth came complexity, division of labor, trade, religion, and governance. Humans were no longer just part of ecosystems. They were reshaping them, clearing forests, diverting rivers, and domesticating landscapes. The Holocene was also an age of invention. Writing emerged in Mesopotamia, allowing stories, laws, and knowledge to endure beyond memory. In Egypt, the Nile's floods nourished fields and inspired monuments that still stand today. The Indus Valley cultivated cities with advanced plumbing. In China, dynasties rose, guided by philosophies and technologies that spread across continents. The Americas built their own wonders: the pyramids of the Maya, the vast networks of the Inca. Humanity was no longer a scattered species. It was a global force. But this dawn of civilization came at a cost. Forests were felled to make way for farms. Wild herds of aurochs, wild horses, and other animals dwindled as domestication and hunting took their toll. Rivers were dammed and diverted. The balance of ecosystems, so delicately maintained through millions of years, was disrupted. For the first time, a single species began to alter the planet on a scale once reserved for tectonics and ice ages. The Holocene also saw the continued shaping of Earth's geography. Sea levels rose as glaciers melted, swallowing land bridges like the one that once connected Asia and North America. Islands were isolated, cultures developed uniquely, and biodiversity adapted to the changing coastlines. The Sahara, once a green landscape, dried into desert. Forests shifted northward. Humanity adapted alongside these changes, inventing tools, rituals, and stories to survive. The Holocene is a story of creation and transformation. It is the chapter where humans, once prey to saber-toothed cats and towering mammoths, became builders of civilizations, writers of history, and stewards, or destroyers, of Earth's ecosystems. It is the age of art, architecture, and ambition. Yet it is also a reminder: we are the latest actors on a stage billions of years old, heirs to a legacy shaped by continents colliding, oceans vanishing, and creatures rising and falling. The Holocene is not just history, it is the prelude to today, the bridge that carried us from nature's dominion to human dominion. Our journey has carried us across billions of years, from the silent rocks of Earth's first continent, Ur, through the mighty unions of Kenorland, Nuna, Rodinia, and finally Pangea. We've watched oceans open and close, mountains rise and crumble, forests bloom and vanish. We've stood in the shadows of dinosaurs, walked among mammoths, and witnessed the dawn of human civilization. To ask what Earth was like before Pangea is to peer into a story so vast it humbles us. A story of endless creation, destruction, and renewal. What we see, again and again, is that Earth is not static. It is alive, restless, and forever in motion. The continents beneath our feet are fragments of ancient worlds, stitched together by time and torn apart by the deep breath of plate tectonics. Every grain of sand once belonged to a mountain. Every mountain once lay buried in the sea. The land itself remembers. Pangea was not the beginning. It was a chapter. Before it, Rodinia gathered the continents into a barren giant. Before that, Nuna united ancient cratons under dimmer skies. Before even Nuna, Kenorland and Ur marked the planet's earliest attempts at creating permanent land. Each supercontinent shaped the climate, the oceans, and the destiny of life. Each collapse opened new seas, new coastlines, and new opportunities for life to diversify. Life, in turn, shaped Earth in return. Microbes breathed oxygen into the air. Plants cloaked continents in green and cooled the planet with their carbon hunger. Forests of the Carboniferous left behind the coal we burn today. The dinosaurs reigned for ages, only to vanish in a single moment of catastrophe. Mammals rose from the shadows, building civilizations, and now stand as the dominant force on the planet. And here we are, in the Holocene. Or, as many scientists suggest, the Anthropocene, the age of humans. Unlike any species before, we have become a geological force. Our cities glow brighter than stars from orbit. Our machines split atoms, move mountains, and send voices across the world in an instant. Yet our actions also scar the planet. Forests vanish, oceans acidify, climates shift. We are both creators and destroyers, inheritors of Earth's deep story and authors of its next chapter. So, what comes after us? The continents are still moving. In 200 million years, scientists predict they may gather again into a new supercontinent, Pangea Proxima or perhaps Amasia, a landmass yet unborn, surrounded by future oceans. Life will adapt, as it always has. New giants may walk the land, new forests may rise, and Earth's story will continue long after we are gone. The question is not whether Earth will endure. It will. The question is what role we will play in shaping the next chapter. Will we leave behind only ruins and silence, or will we carry forward the wisdom to live in balance with this restless, beautiful world? From Ur to Pangea to now, Earth reminds us of one truth. Change is eternal. The continents shift, the skies transform, the creatures rise and fall. Yet through it all, one thread endures. Life's unbreakable will to survive, adapt, and begin again. And so the story of Earth is not finished. It is still being written under our feet, above our heads, and within us.